In this video, we're going to learn how to calculate the probability of events occurring based on some counting techniques you've learned about in previous units. Counting techniques that involve permutations and combinations. So up until now, your understanding of probability has been that it can be calculated based on the number of occurrences of an event divided by the number of total events, both that do occur and don't. Here we can narrow down this denominator into saying that it is the number of events that can occur with no restrictions at all. So let's take a look at some examples for both permutations and combinations. And let's begin with permutations. So our first example says 5 people are seated in a row in a classroom. What's the probability they are seated from oldest to youngest? So let's imagine those 5 people sitting in a row. And if they are seated from oldest to youngest, there is only one way that that can occur. Or is there? Well, no one said oldest had to be on the left and youngest had to be on the right. Is it also possible to have the youngest on the left and the oldest on the right, in which case there would be 2 ways? Okay? Since this question doesn't specify whether they have to be from oldest to youngest in a left to right or right to left notation, we will assume that there are 2 possible ways for this to occur. So the probability of those students being seated from oldest to youngest would be equal to those 2 occurrences out of a total where there are no restrictions. Well, if there are no restrictions, we know that out of the 5 people, anyone can sit here first. Once that one person has sat, there's now 4 left for this position, and then 3, and then 2, and then 1. And we can show this using the slot method. We can also communicate this as being 5 factorial. So 2 divided by 120 would be our probability, but we always reduce probabilities down to their lowest terms. That would make this a 1 in 60 chance that if those students are arranged from oldest to youngest in either of these 2, there'd be 1 out of 60 chance. If you were to express it as odds, just as a recap of last lesson, we would call it a 1 to 59. Let's look at another example. Let's say that you go to your local fall fair and you play the water cannon game, where you shoot water at a target to try and make a horse race or something climb up to the top the fastest. Let's imagine that there are 7 competitors. I'm going to line them all up sitting beside each other like they would be at the fair. And the question is, what is the probability of predicting first and second place if there are 7 competitors altogether? Well, there can be only one occurrence of who wins first and who wins second, right? You can say this person comes first, this person comes second, done. So as we begin our probability calculation, we can say the probability of first and second place is equal to, there's only one possible outcome. But what are the unlimited number of outcomes? Well, any of those 7 can place first, and of the 6 that remain, any of them can come in second place. Okay? And the question doesn't concern itself with the placings after first and second. So we can express this as having unlimited, no restrictions, in a couple of different forms. And I'll recap that for you. We could write it like this, or we could write it like this, or we could write it like this. Okay, a 1 in 42 chance as a probability. If you were to write it as odds, of course, it'd be 1 to 41. Yes, no, total. Okay, let's move on to some examples involving combinations. Our first example says, from that water cannon game that we just looked at, oh, I'm sorry, I missed the second part of example 2. It says, how does the probability change if you're predicting first, second, and third? Sorry about that, let me go back. If you were doing first, second, and third, you have 7 times 6 times 5. And we're not concerned with the remaining placings. Again, the probability of first, second, and third Well, there's only one way that can happen. Only one person can be first, only one person can be second, only one person can ultimately be third. But what if there are no restrictions in how you arrange those? Well, the only change would be we would have our no restrictions as a permutation written this way, or as 7 times 6 times 5, or 1 210th. Okay. Now let's go to combinations. So back to this game, the water one. What is the probability of choosing the top 3 finishers regardless of their order? So in that case, what that means is that you have your 7 people lined up, and you're right in that only one person can be first, one can be second, one can be third. But what this question is saying, I just want to know who the top 3 finishers are regardless of their order. In other words, order doesn't matter. Well, that's a clue to us that this is a combination instead. So the probability of looking at first, second, and third is still one occurrence. Only one person can actually be in first, second, or third place. But if we're not concerned about order, we can write this as a combination instead of a permutation. And 7 choose 3 comes out to 1 out of 35. Let's look at some more examples. Let's say that you've got a class of 20 females and 11 males. And out of this class, we're going to determine the probability of choosing a group of 7 people. Now within these 7 people, we're going to have a couple of scenarios. So first of all, what happens if there are exactly 3 males in that group? Okay. Well, our probability then of getting exactly 3 males in the group means we've got to choose those males first. There are a total of 11, so out of those 11, let's choose 3. That means that in order to make our group of 7, we need 4 females. Let's make sure that we choose those out of the 20 that are available. And in the denominator, no restrictions. So that just means we're going to pick 7 people out of the grand total of people. The grand total of people is 31, of which we don't care who those 7 people are that are chosen. Okay? If you punch this into your calculator, you can do it all at once if you remember how to use your combination button. I'm going to break it here into numerator and denominator just so that you can make sure you're doing it correctly. So 2,629,575, which as a decimal comes out to 0.304. I'm going to go to a percentage, multiplying it by 100. So it comes out to approximately 30.4%. Okay. In part B, let's go back to this scenario where we're choosing 7 people, but this time there has to be at least 2 females. So we have this scenario where out of those 7, we have 2 females, 5 males, 3 females, 4 males, 4 females, 3 males, 5 females, 2 males, 6 females, 1 male, or all 7 females. Now that's a lot of scenarios. And it can be solved directly, but I like to propose that for this one, it actually might be easier to solve if it's done indirectly. So the probability of choosing at least 2 females, I've written that as females have to be greater than or equal to 2. And this time I'm going to work with decimals. So here is no restrictions, all scenarios. Let's take away the probability as a decimal where there are no females in the group. And then let's also take away the probability where there is only 1 female in the group. Because what's left over after we subtract from the whole then should be all the scenarios where there are at least 2 females. So the whole means, again, no restrictions. So 31 people, let's choose 7. If there are no females, let's ensure that happens. Let's take no females. That means of the 11 males, 7 will be chosen for the group. In this scenario, in order to make sure we get our 1 female, let's make sure she's chosen first, and then the remainder of the group has to be from the males. Now each of these can be individually divided by the no restrictions, or because the denominator is the same in every case, we can do the subtraction and divide by that no restriction value in the denominator. Okay? Again, you can do this all with your calculator, but if you do, be very cautious that you want to solve for the numerator before you do the division. Okay? Otherwise, you'll only be dividing this last term by the denominator instead. Okay? I'm going to break it down into numerator and denominator so you can make sure that you're doing it correctly. However, I do encourage, if you can do it all in one step, go for it. Just be mindful of your usage of brackets. So as a decimal, this comes out to 0.996. I'm going to multiply it by 100 and get 99.6%. Now it makes sense that most of our scenarios out of the 31 choose 7 will have at least 2 females because look, the greatest proportion of those 31 people is females. It's quite high as we can see. All right, let's try one more combination example. We're going to go back to cards. The game of bridge is a game where you take all 52 cards and divide them amongst 4 players so that each player has 13 cards. Okay? What is the probability that you get dealt a hand that has 3 queens in it? Okay? Out of your 13 cards. Well, if we're going to figure out the probability of getting 3 queens, we need to make sure that those 3 queens get chosen first. So how many queens are in the deck? There are 4. So let's make sure that 3 of those 4 queens get chosen. That means the remainder of your hand, the other 10 cards, have to come from the remaining cards. Okay? And this will ensure that the other queen is not chosen. So let's make sure that we have 52 minus 4. Okay? Again, that queen will be out. The remaining cards will all be from the other values of cards. Now, if we don't care what your bridge hand looks like, your 13 cards, no restrictions, we can just say 52, choose 13. If you calculate this, you'll get a decimal of 0.0412, or you can express it as a percentage, 4.12%. Now, you can have some fun with card hands as well that is not included in your note. We could say, what about probability of getting 4 of a kind? And I'm just going to do this as an asides, right? If you want to get 4 of a kind, then first of all, you're going to choose the value of the card that's going to be 4 of a kind. In the deck, there are 13 different values of cards from ace up to king. Let's make sure we choose that kind first. Then, within that kind, there are 4 cards. Let's make sure we choose all 4 of them. Okay? In terms of what's left, if you want to let me back up for a second. I got my train of thought. This is for bridge. Let's spell it correctly here. This is for poker. My bad. So in poker, you have a 5-card hand instead of a 13-card hand. Okay. Let me backtrack. So here you've got 4 cards in your hand. They are all of the same kind. You need 1 more card. How many cards are left over that you can choose that additional card from? Well, if you've got a 4 of a kind, you've got 52 minus 4 here as well, being the remaining cards that you can choose 1 more from. If you have no restrictions on this 5-card hand, then you can go 52, choose 5. When you punch this in and multiply it by 100 to express it as a percentage, you get about 0.024%. And you can appreciate that getting 4 of a kind in a hand is a pretty tough gig to get, and the numbers show that as well. All right, for fun, if you like a challenge in terms of probability calculations, there's a really fantastic example on page 323 in your textbook that I encourage you to read and have some fun with. It asks the question about what is the probability of two people in a classroom sharing the same birthday. And that will depend on the number of people in the class for sure. But go take a look at that example because it's kind of fun. All right, have fun with your practice and let me know if you have any questions.